Here's our fourth example of sketching the graph of a rational function. This one is x squared minus x minus 6 all over x squared minus 9. As we've done before, it's useful to try to factor the numerator and denominator if we can, and this one factors nicely. It's x plus 2 times x minus 3 over x minus 3 times x plus 3. Now in this particular function, notice that the same binomial exists in the numerator and the denominator. And that's going to be called a whole at x is equal to 3. What's going on here is that there's no vertical asymptote and there's no zero of the function because as x gets closer and closer to 3, both the numerator and denominator do the same things, and so that action on the function graph sort of cancels itself out. So this will be called a whole, and we'll see what that looks like later. So we'll proceed pretty much as usual. We'll find the y-intercept, f of 0, and that's just going to be minus 6 over minus 9. So that's going to be 2/3. So we'll sketch that on this graph. Make sure to label the axes. This is going to be 1, and that's roughly 1/3 and 2/3. So here's 2/3. We know the graph is going to pass through that y-intercept. We'll find the zeros by looking for the zeros of the numerator. And we've already factored that numerator, so we know that those are zeros at -2 and x equals positive 3. So we'll sketch those out. So here's -2. The function is going to pass through there, and positive 3, the function will pass through there. Although we know it has a whole at x equals 3, so we'll have to deal with that. The vertical asymptotes are the zeros of the denominator, and they are going to be plus and minus 3. So we know that there's a vertical asymptote at -3, but not one at x equals 3 because we know we have a whole there. So we have one vertical asymptote at x is equal to -3. Now the shortcut to the horizontal asymptote here, and with all rational functions that look similar to this, is that the degree of the numerator and the degree of the denominator are the same. And so if that's true, then the horizontal asymptote is just the ratio of the coefficients of those, which is 1 over 1, or 1. So there's a horizontal asymptote at y equals 1. Okay, so let's start to graph our function. We know that it passes through the x-axis at -2, but not at 3 because 3 is a whole. It goes through our y-intercept, and it has to behave asymptotically at this -3 vertical asymptote. So this looks pretty good so far. Now, as for what's going on the left side of that vertical asymptote, we should just calculate a point quickly. So let's do f of -4, and that is going to be 16 plus 4 minus 6 all over 16 minus 9, and we want to know, is that greater than or less than 1, the value of the horizontal asymptote, and it's positive 2, so it's greater than 1. So the function has to live up here in this area. It's never going to cross the x-axis again. We're out of roots. And then we finally have to go in here and put a hole at 3. This is a place where there is no value of this function. The function can't have a value of 3, otherwise it would be infinitely large. But there's no sort of asymptotic behavior or anything like that. So holes in functions are kind of interesting, but once you get used to them, they're pretty easy to deal with. Let's look at a calculated version of our graph. And it looks pretty much just like our sketch. Here's our horizontal asymptote at y equals 1. And we have our hole over here at x equals 3. And that hole, by the way, is not going to show up on a calculator or computer graph unless it's very, very sophisticated.